Hello guys and welcome back to my channel. So in this video, we are going to dive into the architecture and evolution of JS Mentor, a project that started out as a neat single-tiered web app and grew into a fully fledged AI and ML powered learning management system. So let's be honest for a second. 4 months ago, JS Mentor did exactly what a lot of modern portfolio projects do. It took user input on the front end, wrapped them in a clean in component, and handed them off directly to external API like Clerk or authentication and Grok AI to handle the thinking. It worked, it was snappy, and it looked great. But as I kept building, it actually hit me that this application completely lacked the actual essence of an LMS. A true learning management system shouldn't just act as a glorified wrapper for a third party AI chatbot. A real educational platform needs context. It needs structural memory, and most importantly, it needs to actively understand student progression over time. In a single tiered setup, if a learner hits a brutal loop error or runs into rate limiting constraints, the platform has zero historical awareness of that struggle. It cannot trace behavioral telemetry, it cannot track metrics like time spent on a complex topic or problem, compiler execution failures, or sequential quiz iterations. So I decided to pull out the plumbing, move past basic API delegation, and spend the last 4 months re-architecting this into a multi-tiered software ecosystem. Today we are deep diving into how a dedicated async FastAPI backend, real-time WebSocket traffic controllers, native WebRTC video channels, and a custom Scikit-learn predictive modeling pipeline work together under the hood to flag academic risk before a student ever fails. So without further ado, let's jump in. This project actually started out as a small favor. A friend of mine was actually struggling with a minor project submission and he handed me this repo that was forked elsewhere from GitHub. And my job was simple, just make it functional, get all the features running and deploy it. But while I was working on it, I got really invested and I saw potential here, and I just wanted to experiment a bit with AI and ML integrations inside an LMS. So after I handed the finished project back to my friend, I kept working on it myself. I began adding extra functionalities, new modules, and slowly it grew into something more than just a submission. That's how JS Mentor started evolving into the project that you are seeing today. So this here is the landing page of JS Mentor. I think I have shown a demo for JS Mentor in the previous videos as well, but I have done quite a lot of changes on the front end. I'm just scrolling down. So basically JS Mentor has two entities or two actors. First one is the student, and then there is the trainer. So basically trainers and students interact with each other with the help of our platform. So first of all, we will be talking about the student role. So student authentication is pretty much simple. You just have to click on sign up or login, whichever you would like. We have used Clerk here, so you can actually go ahead and continue with Google straight away. I'll choose my ID, and so yeah, this is the student dashboard. As you can see, there are some learning insights over here. This is basically a way to show how much progress we have made across our learning paths. So this over here under the curriculum mastery is the accumulative of all the learning paths, and below there is the separate learning path. So the statistics are shown both way, and there is the final examination over here which is locked, and it only opens after you have completed the 6 learning paths. Then only the assessment will be open and you can give the assessment there. This over here is the upcoming doubt session. So we have added the functionality of having students actually request for doubt session and schedule them. So if the student has any doubt sessions scheduled, it will show up in this section of the student dashboard. Now moving on to the learning paths, which contain all the curriculum. So we have 6 learning paths, as you can see: fundamentals, JavaScript core, front-end framework, Node.js, full stack architecture, technology and trends. These are the 6 learning paths that we have. So I have not changed a lot with respect to the curriculum. Inside these paths, I have actually added more things in it. First of all, I have added quizzes to each learning path. Then I've added exercises, and also I've added videos. So basically, a trainer can actually add videos to every learning path. So we will be seeing that when we will be talking about the trainer role. Now, as you can see, I have changed some CSS and some styling for the front end. And this is the path progress, which reflects over here in the sidebar as well for the particular learning path. And this will be reflected in the dashboard that we just saw. So basically, we are using intersection observer and mutation observer to basically map how much progress a particular student has made. For example, when I scroll this page all the way down to below, I have actually completed reading all the contents of this page. So this will be changed to a particular number. Now it will reflect over here. It shows 30% because we also have the video tutorial over here, the hands-on challenge and the quiz. As I mentioned that these will be added by the trainer. Now some paths may have them, some paths may not. It totally depends on the trainer. We have given that flexibility to trainer to assign these things. So basically, if you move to this setting up environment page, so in this one, as you can see, there are only hands-on challenge and nothing, no quiz and no video lectures over here. So in this, the progress will be calculated a bit differently. Formula for calculation of the progress we will be seeing when we will be talking about the different modules of a little bit later in this video. So when I scroll up again, you will see that it got to 30%. That progress was tracked over here. And if we move back to the dashboard as well, you can see that this was changed to 19%. Earlier it was something else. You can also verify it by going to this particular learning path which we haven't explored yet. So we can go to front end. We can continue over from here. And now in this page, I can go to below. Now this page doesn't even have the exercise. No quiz, no exercise, and no videos, only this. Okay, there is one simple quiz over here. So if we move up, you can see that this is considered as complete. So the same will happen to other pages which have no exercises and all. If there is an exercise, there is a particular weightage of that here. So we will be discussing about that student progression calculation formula later on in the video. Now moving back to the learning paths overview, you see that we have 6 learning paths over here: fundamentals, JavaScript core, front-end frameworks, Node.js, full stack architecture, technology and trends. Now technology and trends is mostly theoretical part over here, and full stack architecture, Node.js and front-end frameworks. These are really good for curriculum and for initial introduction to these topics. But the problem is we do not have the means to provide our students with the compilers for these. I only have the compiler for performing basic JavaScript operations. So the first 2 learning paths actually have the compiler there. The remaining 4 do not have compiler component embedded over there. So that is the distinction I made, and this pretty distinction has also helped me in determining the threshold for the eligibility for predicting whether a student will pass or fail. So the first 2 learning paths, if the student has completed these 2, only then we will be calculating whether the student is going to pass or fail with help of our ML model, which we will be discussing on later. So that was it about the learning paths. Now I'll show you the compiler real quick. this is the same compiler that we had in the first video that I made. If you haven't checked out that video, please go ahead and check out. So this is pretty much very simple. You can change the mode over here, the light or dark mode, whatever you prefer. So there was some bugs in this compiler as well. So I have tried to eliminate most of them, and I think there are no bugs as of now. So if you type in some code, it will be reflected over here. So when you write document.write, it will be presented in the UI output. And if you write console.log, that will be done in console.portion over here. So that distinction I had to program myself. And also if you use the three notification functionalities like alert and all, the program the platform actually showed them over there on the top of the page rather than in the output. That is still to be corrected, but other than that it is all good. And you can see that I can type document dot write, and inside I can pass a message, and this will be deflected in the UI output, as you can see. And also if you make some mistake, like I have done this typo, now I will not get any UI output, right? So for this also there is one simple thing that we have added. For example, if I write console.log and then I will just give n. Now right now, as you can see that the error is giving, the explanation is given that n is not defined, and this is pretty much self-explanatory that we had to define n over there. But consider if you have written a very big code and you cannot figure out the error with the help of just this simple message. So you can click on this explain error, and it will actually invoke the LLM API and the domain specialized AI assistant that we have created, and it will pass on this log of the error as well as your code to it and ask for a better explanation. So the short explanation over here is given is the error happens because n is used before it is defined. In JavaScript, you must declare a variable let const or var given it or give it a value before you can log it. So this is the corrected code. You can actually copy it and you can paste it over here. That way you can actually correct your code. So it helps you write your code. It will not be giving like the complete code by itself. So we are promoting students to write their own code rather than just relying on AI. This is different from VS Code or other AI IDs in which you just have to write a particular command to invoke the autocomplete functionality. So that is there about the compiler. Okay. So now if you scroll down to this particular quiz and this exercise, and if you click on solve challenge, here the compiler is a bit different. If you have noticed that there is over here a warning level displayed. So this is because we have created an anti-cheat engine which actually stops you from using different means to cheat. For example, this new Ask Gemini feature that is now coming in Chrome with the new release. If you click on it, a new sidebar opens, and as the new sidebar opens, we can actually see what's going on the screen or on the web page, and we can ask this to Gemini and it will give you answer, and you can just copy it or you can just type it out because paste is not also allowed over here. So you can see that it has given us that workspace blocked, external sidebar, split screen or developer tools detected. So it is giving you clear message, and this is the first warning actually. After there are 2 or 3 warnings, it will actually close this particular exercise for you and you will not be able to submit your solution then. So I'll just close it now. And as you can see, switching tabs of window is recorded. So we have gotten two warning levels over here because we did not close it right away. And so it will have a basic task, of course, because it is an exercise. So we just had to log hello.js mentor to the console and use alert to show welcome to the course. After doing this, you can just click on submit solution and it will be sent to the trainer dashboard, and the trainer can evaluate your particular code and give you marks accordingly. So that is the basic idea of having exercises over here. Basically the essence of it. I'm just going to close it now. I've closed it, and I'll also show you how the quiz works. So this is primarily a basic quiz view. So which method is primarily used for debugging the browser console. We can go for console.log, and along with this we have also added the feedback or appreciation over here. So if you give a correct answer, it will give you a particular encouragement like great job, this the go-to for you were right and all of that message. And in case if you give a wrong answer, it will give you the explanation for it. And this is all happening in real time. We have not stored all these responses. So for example, what does this alert function do? So it basically displays a pop-up function, but we are going to say it saves data. Now this is wrong. So we got a bigger feedback over here, and it explains everything about the alert function to us. So this is happening with the domain specialized AI assistant. Now I'll just be going to move to another page. I'm not going to complete this quiz. So let's move back to the dashboard. So in the dashboard, there are also notes, as you can see. So there are some PDFs attached right now. So these PDFs you can download and you can see what particular notes are provided by the trainer to you. Also, then this chatbot is not just an AI assistant anymore. We have added the functionality for doubt session scheduling over here. So for example, if I have a doubt in Node.js and workers, so I can just request doubt session, and now I have to submit this doubt in the input area itself. So I'll just click on submit doubt. So my doubt session was registered and I have the notification for it, and a 30-minute session will be scheduled for you. Check my sessions for update. Now this my session is in the dashboard, as I already told you, and see that there is one doubt session over here, and the mentor has not been assigned yet because there is no mentor online right now. So there is a particular scheduling algorithm which works automatically in the background. We will be discussing it when we will be taking up the trainer module, and you can see the date, and I mean the schedule is still awaiting to be allocated. When the doubt session is actually scheduled, you can actually connect to it yourself, or the trainer can actually invoke it, the particular session. So it can happen both ways basically. So that was pretty much it about the students end. Let's now talk about the AI assistant. In the last version I actually checked, and when we talked about like a really big response or a really big question that need to be answered, there were some issues with the CSS, and now I have actually fixed them. Like for example, let me just have over here that tell me about the history and evolution of JavaScript. So this will actually give us a really big answer, since both history and evolution are to be discussed. So as you can see, it has given a particular table. And it has given year-wise account of how JavaScript evolved. So the core drivers of JavaScript growth, and then also some chronological narrative. So you can see that the code was actually given in a particular code block. So this is pretty much perfect. You can see there is no CSS leak over here. And if you want, you can ask a follow-up question as well. This was not in the previous version, so this is actually added here. Now let us look at this from the trainer's angle. So the authentication for trainer is going to be a bit different from the authentication for students. So for this, I'm just going to click on sign up, and down below you can see that if you're a trainer, you can sign up here. Now I'm going to create a new account. So I'm going to name it as Vedant. And here I'll use this ID. The phone number you can give anything. Okay. I'm going to change the password. And here is the difference between the student and the trainer authentication. So trainers basically have a separate registration code. So this registration code is going to be in a specific format basically. So once you click on register, you will be redirected to the login page now. Now I'm going to just click on sign in. And you see that I have been redirected to this trainer dashboard. So here are some sections. We will be looking at them one by one. So here you can see that there is one message, welcome back. And then you can see over here is the offline button. So whenever a trainer turns this on, the scheduling algorithm starts working. And once the trainer is online, it will start scheduling the doubt sessions for the particular trainer. So let's turn this on to online. And you can see that there are some statistics over here, the number of active students, the pending reviews, the new doubts. You see that there is one doubt over here, average score, and the submissions will come over here. The exercises that we saw in the learning paths are the submissions for those will be reflected over here, and active mentorship sessions will be reflected over here. Now, this was overview. Now we move to student progression. So in this, what we get is we get the cohort average. So like if you have like 150 students over here, so all of their average is going to be calculated over here and it will be shown here. So it's basically progression, but from the trainer's perspective. From a student's perspective, it is more personal. So they have their own separate progression for themselves. Now trainer has the progression for the entire cohort. So right now it is showing 0% for all because there is only one student over there. And also the exercise success rate is calculated and the cohort average score is calculated. Also, I've added the AI predicted high risk people over here. So right now there are no high risk parameters that were triggered. So we will move to grading hub. Now in grading hub there, since there are no submissions, so that need to be graded right now. So it shows no submission count. But as soon as you submit a particular exercise, that will be reflected over here in the grading hub. Student doubt session, as you can see, there is one doubt session and it didn't reflect over there in the overview as active mentorship session because we haven't been assigned it yet. Now, when I click on this, I can actually start talking to the student and I can also resolve this and I can also change it into the video call. So this is basically on the basis of the difficulty and on the explanation required for the particular doubt. Then in curriculum, we basically have the syllabus, and these are basically the learning paths that we just saw. So if you want to edit this particular path, you can just launch the syllabus editor. So you see that this path opens up like this. So you can change the topics or the introduction or the description to them. And as well as the code blocks, if you want to change the example code that we have given. And herein you can see the live preview of the changes that you have made. So this is better if you do not want any mistakes and all. Have the preview over here. Now you can save path after you have done the changes. I'll just close it for now. Also, you have given the functionality to add an entirely new path. So when you click on this add new path, you open this separate window in which you can add a new path. So you need to give a title and description and the topics and all of that. So you can do this as well. I'll just close it again. Now moving to the risk analytics, as you can see that right now there are no students that are flagged as high risk. So that is about it. But as I've said, after doing the first two learning paths, after the student has actually finished the first two, they will be assessed from the ML engine. And if they show any risk, they will be reflected over here in the dashboard, and the trainer can intervene at that point. They can connect with them, or they can talk to them about the problems they're facing, or resolve any doubts that couldn't be resolved during the doubt sessions, or help them in general, basically. Now, coming to the last section is the video tutorial. As you can see that we have added two videos over here. These are published. So if you want to add a new video, you can give it a title over here. Then you can add a video from YouTube, or you can upload a local video as well. So you can assign it to whichever learning path that you want. So for example, if I take a YouTube video URL, so I've added one YouTube URL and I'm going to give it a title, Learn JS in 1 hour. And this title, I want to add it to a particular learning path. So I'll just choose the fundamental right now. And now you have to choose the topic as well. So I'm going to go with JavaScript basics. Now I can click on save and publish. So as you can see, this published tutorials. Now, if you want to verify if this has been really published in a learning path, you can go to learning path. And the topic was JavaScript basics. So as you can see, if you scroll down, you'll see the video tutorial added over here on the website. Similarly, you can add a local video as well. So for example, I'm going to add this file and I'm going to assign it to technology and trends. So in technology and trends, I'll just go with JS technology and trends. I'm going to save and publish. So now what happens is the local video isn't going to get saved to the server or the backend that we have created. It is going to Cloudinary. So we are making use of a third-party application, Cloudinary, that is going to help us with the video rendering and storage as well. Okay, so now let me demonstrate how the doubt session and resolution works. So in the right side, I've actually opened a tab with student login. And in the left section, you can see an incognito window with the trainer login. So I'm going to just open this chatbot and I'm going to register a doubt. And I'll wait till the doubt session is registered. So you can see that your doubt has been registered. A 30-minute session will be rescheduled for you. Check my sessions for update. So I'm not going to check my own session. I'll just refresh over here in the trainer dashboard. And now you can see that one doubt actually has appeared in my sessions. So the scheduling algorithm has worked. So basically, you do not actually need to refresh this on your own. It auto refreshes in a while, but sometimes it takes time. So you can manually refresh data from over here. So now I'll just click on new student and you can see that no messages have been sent yet. So I'll just initiate the conversation from the trainer part. So I'll just say hello and it will be coming over here as the notification and in the chatbot as well. Hello. So I'll just reply hi sir. And this is all happening in real time. So this is seamless. As you can see, what is your doubt regarding? So you can see that the message comes and this automatically scrolls down, and I'll just reply the MJS format and how module works. So likewise, you can actually put out your doubts and you can talk to the trainer, and then you can also upload image to actually show in what certain part of the code you have a particular doubt. So the image will be sent to Cloudinary server again, and we have actually ensured ephemeral storage for images so that after the session is over, they will be automatically deleted, and we do not clutter the Cloudinary servers with the images that were done. After the resolution is met, like for example, from over here, if I click on resolve, this session will be finished, and you can go back and you can see in the student doubt in the trainer dashboard as well, there is no session reflected over here because the session has been resolved. So they do not have a session anymore. So in this stage, all the images from the over there are going to be deleted. First, let's look at how the data securely flows. When a student authenticates via Clerk or Google OAuth, our FastAPI gateway intercepts a backend webhook on user.created to provision state tables automatically. The client communicates purely with our internal gateway via standardized JSON data contracts. The trainer onboarding process enforces strict access control. When a prospective trainer attempts to sign up, they must provide a pre-authorized registration code. The system validates this code format. Invalid codes immediately block the registration attempt. Valid codes proceed to a custom backend authentication API, which creates the specific trainer account and links the consumed code. Subsequently, the trainer can log in using their newly created credentials to access the specialized trainer dashboard. Now, once a student logs a doubt, how do we route it to an instructor without causing massive scheduling chaos or trainer burnout? To handle this, I engineered a custom backend routing script built around a saturation and dynamic backfilling strategy. Let's trace the algorithmic flowchart to see how exactly it processes requests. Every time the engine fires up, the very first thing it checks is a strict calendar boundary. Is it a Sunday? If yes, the run immediately terminates. No session are scheduled, protecting trainer downtime. If it is a weekday or Saturday, the engine proceeds to fetch data, pulling all active unresolved doubts, matching them against our pool of available trainers. The engine picks up pending doubts using a strict FIFO priority model to ensure the oldest request gets answered first. Before it can map a time slot, it checks the curriculum architecture to calculate the session length. If a student is working on basic concepts in learning paths 1 or 2, it carves out a 30-minute block. If they are grinding on advanced concepts in path 3 through 6, it dynamically provisions a full 60-minute debugging window. So this I have done with a 2-level classification mechanism to ensure whether the doubt belongs to the learning path 1 or 2 or 3 to 6. First, we basically fetch all the topic names of the learning paths with the help of an API. If the query contains keywords for that match with any of the topic names, we can determine which learning path they belong to and hence allot the time slot accordingly. If the user's query doesn't match any topic names, then we let the LLM decide which time slot the student should be allotted. Standard web apps usually load balance, meaning they distribute tasks evenly across everyone. But to maximize efficiency, our algorithm does the exact opposite. It sorts active trainers by their already booked minutes in descending order. The engine intentionally tries to completely saturate the shift of an instructor who is already working up to their maximum 6-hour daily ceiling, which is 360 minutes, running from 10 to 4 p.m. This optimization keeps your backup trainers completely unburdened and free unless cohort volume absolutely demands it. Once a trainer is picked, the system runs a capacity validation. This engine doesn't run on a slow cron job. It reactively wakes up the exact millisecond a student files a ticket or a trainer clicks resolve. keeping students wait time incredibly low. For implementing this whole automated scheduling, I have made use of APS scheduler library in Python. Now that we have seen the algorithm, let's take a look at the doubt resolution lifecycle. It begins when a student registers a query providing a topic and description. As previously mentioned, a hybrid classifier categorizes the doubts and assigns a priority. Our automated scheduling engine then processes the queue with a saturation strategy, finding the earliest available slot for an active trainer and assigns the session. Both the student and trainer are notified and join a synchronized mentorship chat room for text and image exchange. The trainer can escalate this chat to a live WebRTC video and screen sharing session for hands-on debugging. Once the issue is solved, the trainer marks the doubt as resolved, concluding the session and automatically updating the student's progress metrics. Now let's look at how the platform handles image when a student shares a screenshot of their code error. Sending large file over the internet can easily slow down a system. So I designed a smart, lightweight handshake to keep things running at lightning speed. Think of it like getting a temporary security pass at a gated community. When a student drops an image into the chat, the frontend quickly asks for backend for a secure digital stamp of approval. Once our server verifies the student is allowed to be there, it gives them the stamp. The student's browser then bypasses our main server completely and uploads the image directly to a specialized CDN. Our main application server never has to process or carry that heavy image file. The chat system simply passes a lightweight text link to the trainer who sees the image pop up instantly on the dashboard. Now we also don't want this temporary debugging screenshots cluttering up our storage forever and costing us money. The absolute second the trainer clicks the button to mark the doubt as resolved, an automated cleanup worker makes up in the background. It instantly destroys that specific chat session's storage folder, permanently erasing every single image from the cloud. The platform gets completely wiped clean the moment the session wraps up, leaving zero storage debt behind. Let's talk about a major problem with standard edtech platforms: progress spoofing. In most traditional LMS applications, a student just clicks the next button, fast forwarding a video, or scrolls straight to the bottom of the page to trigger 100% completion. They get the green checkmark without actually learning a single thing. To prevent this from happening, on JS Mentor, I built a hybrid multi-weighted strict progress tracking engine that securely syncs real-time browser behavior with our backend database. Here's how a topic's mastery is truly calculated. First, we handle the conceptual side. Theory reading, which accounts for 30% of the total progress. Instead of relying on a simple page loader timer, the frontend uses a native browser API called Intersection Observer. As the student consumes the technical documentation, this observer tracks exactly which content blocks are active inside the visible viewport. If they don't actually scroll through and expose the reading modules to the screen, they don't get that 30% credit. But reading alone doesn't make you a developer. That remaining 70% of the score is heavily weighted towards exercise mastery. This is calculated programmatically by taking the exact ratio of successfully solved coding challenges embedded on that specific page. This brings us to the centerpiece of our platform's intelligence, that is the predictive machine learning engine. To build an early intervention pipeline that actually maps behavioral patterns instead of loose demographics, I have generated and published a highly correlated, mathematically sound training dataset. The student performance prediction dataset is live on Kaggle. If you want, you can go ahead and check it out. Also, you can check out a small working implementation in the adjoining Kaggle notebook that I have added. As I said that to build this dataset, I didn't just throw random numbers into a CSV. I wrote a Python script that simulates how real students behave inside an LMS environment. Let's look at the script once. So first we import some libraries, CSV to write rows into a CSV file, random to generate some random values. Then I've used math for mathematical functions like exponents. Looking at the code first, you can see that there is a function called sigmoid which defines the sigmoid function, the core of logistic regression, something that is going to be used for this model. It takes any real number x and squashes it into a probability between 0 and 1. And now coming to the next function that you see over here is generate realistic data. This is the function to generate synthetic data. So by default we are passing num rows equal to 5000. That means 5000 rows as default this function is going to give it to us, and we are going to save the output in the synthetic training data.csv file. The headers list over here defines the column names for the CSV file, that is the student ID, progress status, time spent, etc. Let us understand what these headers signify and why they are there. So let's look at these attributes one by one. So first is the student ID, self-explanatory. As you can see that this is going to be a unique identifier for the student. And then there is the progress status. So this is going to be the categorical state of the student's current module. So for example, there is going to be 3 states over here, that is completed and in progress and not started. Then after this there is going to be the time spent in second. So this is going to be the time spent on the particular topic or problem in the compiler. Then there is going to be the average exercise attempt. So for a particular exercise, how many times the student actually attempted it, I mean how many times it took for a student to particularly figure it out and then solve that and submit that. Then there is going to be the average exercise execution time. So for example, a student completes like 5 exercises, so that the particular time took for completing those 5 exercises will be averaged. So this basically will identify how fast the student's code executed, and this in turn tells us about the code efficiency. Then there is going to be the exercise is correct ratio. So this is going to be the rolling average of the first attempt correctness. Next is going to be the quiz score, which is basically the final or the current score of the module's assessment. Next is going to be the number of students that has attempted the quiz, which is named as the quiz attempt number. Then there is going to be the predicted pass possibility or probability. So this is the raw output of the sigmoid generation function, and it will basically tell us the particular student's passing probability, whether he is going to pass at 90% probability or there is 40% probability and so on. Then there is going to be the risk level. This is basically the output variable or the target variable that we are actually trying to figure out, and this is basically going to be assigned in 3 classes. First is high, medium and low, and these are assigned based on the pass probability which we just discussed over here, which is predicted by the model. So the model basically will tell us if the particular student has a high passing probability or medium passing probability or not. So that is going to be the data set. Getting back at our script, we now open the CSV for writing and write the header row first. So once these header rows are written, we are going to open one loop, and we look through each student ID from 1 to 5000. We then are going to generate a hidden aptitude score using a Gaussian distribution where mean is 0.5 and standard deviation is 0.2. It clamps it between 0 and 1. This aptitude is going to basically drive all other features. So if a student has high aptitude, they'll naturally spend less time on exercises, need fewer attempts to solve the particular exercises, and then score higher on quizzes. If their aptitude is lower, the opposite happens. To keep things realistic, I have also added some Gaussian noise. That is a fancy way of saying I have sprinkled in some randomness around the averages so that the data doesn't look too perfect and we prevent it from overfitting. Also, this is going to clamp between 300 and 20,000 seconds because this is going to be pretty random. So we need this big range. Then also, as I previously said, that better students need fewer attempts to solve the exercises. So we clamp these between 1 to 10. So the average exercise attempts will be maximum of 1 to 10 over here in this line. Then next we are going to check out for aptitude. So higher aptitude means faster code execution as well. So the range is going to be between 500 and 10,000. And we are also going to add random Gaussian noise as we have already did. Then the ratio of first attempt correctness, for that we are going to go again with the logic that higher aptitude, that means closer to 1. Then after that, for quiz score, so quiz score basically scale with aptitude. So the range we have given over here is between 0 to 100 along with the Gaussian noise. Then stronger students also need fewer quiz attempts. The range for quiz attempt number is going to be 1 to 5. Now this here starts our actual logistic regression formula. So we combine features into a single score Z, positive weights for good signals, that is like completion, correctness and quiz score that we have added over here, and we add negative weights for bad signals like too many attempts are there. So we have added Z minus equal to average exercise attempts multiplied by 0.3. Then we are going to pass Z through sigmoid. So the probability becomes between 0 and 1 and we round it off to 3 decimals as well. Then you can see that this if else conditional tree is present over here. This is going to classify risk based on the probability that is generated. And there is going to be a bit of a threshold over here. That threshold, accordingly we finally write all these student data into the CSV with the writer.write row method. So we are going to write all the data that is generated into the CSV and we are just going to print that this is successfully generated. So that is the basic script behind the dataset generation. Alternatively, you can make use of this other script to generate the dataset, in which we are actually leveraging the LLM to generate the simulation data by prompting it. So as you can see, there is a huge prompt that I've written over here. And also I've actually given some logical rules for correlation. So likewise, it will generate us the data. All right, so now we have prepared our data and now this data is going to hit the actual brain of the system. That is the logistic regression model. So the name logistic regression can be quite confusing and it would lead you to think that it does what it says, regression, that is the prediction of continuous numerical values, but it doesn't. So even though it says regression, we use this algorithm for classification task. In our case, we are classifying a student into low, medium and high risk categories. Here is how the math actually plays out under the hood in a way that makes sense. The model assigns a specific importance weight W to every prepared feature we give it. Think of it like a heavy stakes game. Maybe it can be a tug of war. So on one side, we have features that represent strong student mastery. For instance, high quiz score or high correctness ratio that we just calculated and we just saw at the dataset. This will pull the student towards the safe side, and the model recognizes this by giving these features a positive weight. On the other side of the rope, we have features pointing to friction. High exercise attempts, repetitive compiler failures, or massive submission delays will aggressively pull the student towards the risk side. The model flags this by calculating a negative weight. The algorithm multiplies each piece of live student data by its respective weight, sums them up and gives us a new raw score. We call it Z. So it is now time to understand how logistic regression really works. So first we load the synthetic data that we just generated through our script. Then we pre-process the data. So in the pre-processing, there are basically two things that we majorly do. If the data is numeric for some attributes, if they are numeric, so they undergo scaling. So the scaling is the process of basically shrinking the numerical values. Like for example, if the total time spent on a particular quiz by a student is 300 seconds, no, that is okay. But for some student that is not as efficient or as learned as that one, the time can be a lot more, like 900 seconds or even 1,000 seconds or 16,000 seconds. When you feed this data directly to the model, it will get confused between the two numbers. It will think of the numbers as the higher the numerical value, the more prominent it is, which is not the case in this feature. So we need to shrink these values within a particular range. So like the standard scaler will actually shrink them to values like 1.5 and 0.2 and such. And then there is one hot encoder for categorical attributes. So if the attribute is particularly like in classes, like for example, in our case, we had like not started, in progress, and completed, those three stages of exercise completion, I think. So in those categories, we need to translate that into numbers. So one hot encoder basically does that itself. Then after that is done, we feed it to logistic regression model, and the model is trained and is saved as risk underscore model.joblib. Now, at the inference time, what happens is we load this model dynamically. So in inference phase, what happens is we have the system database and it is continuously being updated with the student progression. So we first check the qualification. We are not going to check every student for the risk of passing or failing. So there is one threshold that the student must have completed the first two learning paths. If those are completed, we will be checking if the particular student is under risk. So once we start checking it, we check the time spent, the attempts, the correctness ratio, quiz scores, etc. Then we dynamically load our model, and the model will be predicting the probabilities to us. And if the risk level is high, it will flag the students on the dashboard, on the trainer dashboard. Code safety isn't just about runtime tracking, it's about assessment integrity. To guarantee that students are writing original logic, we built a native anti-cheat proctoring engine right into the component lifecycle. The editor hooks directly into the standard browser window states. If a student loses focus on the programming canvas or switches tabs to scrape solutions from a side window, the engine intercepts the native blur and visibility changes window event. Each violation increments a tracking variable state, warning the user via persistent modal alert. If a student triggers more than 3 security flags, the workspace locks down automatically, closes out the interface, and marks the exercise evaluation status as unverified infraction or for manual trainer audit. So let's move on to how the platform handles core content delivery, that is, video tutorial management. When building an LMS, instructors need complete flexibility. Sometimes they want to upload custom proprietary MP4 videos directly to the platform, and other times they just want to link existing public resources like a YouTube tutorial. To solve this, I designed a dual stream media architecture that handles heavy local media hosting via Cloudinary and external assets via YouTube embeds, while treating both identically on the student's front end view. Let's look under the hood of how local video uploads function. When an instructor uploads a new raw MP4 file, the frontend wraps the metadata and the file binary inside a standard form data object and shoots a post request to our backend. Now, instead of choking our FastAPI application memory by writing massive binary media streams to our server disk, the backend acts as a secure non-blocking proxy. It instantly pipes the file straight to Cloudinary storage servers. Cloudinary gives back a secure delivery URL, which we store cleanly in our PostgreSQL database. But here's the real trick to maintaining ultra-fast dashboard page load times. Instead of forcing the browser to download heavy video files just to display a preview icon on the dashboard, we use Cloudinary's dynamic transformation parameters directly inside the image URL strings. By simply appending tags, we tell Cloudinary's edge servers to scan the video file, automatically pick an optimized visual frame, scale it down to exactly 500 pixels, and render it as a lightweight image poster frame. On the student side, the application loops through these paths and plays them seamlessly using the native HTML5 video containers. What happens if the instructor drops a standard YouTube link instead? This triggers our zero storage embed pattern. We don't want to waste computational power or cloud storage space downloading a video that Google is already hosting for free. The moment a trainer pastes a typical YouTube watch link, a string manipulation utility on our frontend instantly sanitizes and reformats the URL string into a clean embed structure, which is then stored directly in the database. But remember, we still need a dashboard preview thumbnail for this video. Since we aren't using Cloudinary here, we bypass complex YouTube API keys entirely. The system extracts the unique video ID from the URL and pulls the medium quality static poster frame directly from Google's public asset delivery network at img.youtube.com. Finally, let's understand how this plays out on the student screen. When a student launches a YouTube tutorial inside our video carousel, the frontend doesn't just display a lazy iframe. The system dynamically appends a specific query parameter to the end of the video link. This little flag is crucial. It activates the YouTube's internal JavaScript API layer inside the container window. This allows our React application to actively listen for video event loops, like when the video starts, pauses, or finishes. The moment the player registers a complete view event, it fires a progress trigger back down to our database tables. By combining direct cloud storage, delegating with smart string sanitation, our media platform stays incredibly fast, highly scalable, and completely adaptive to how instructors want to deliver their content. That, guys, is the complete structural lifecycle demo of JS Mentor. By introducing that asynchronous FastAPI backend along with the predictive ML model and a lot of amazing features, we have turned a standard coding tool into a high-touch, context-aware LMS ecosystem. If you're a developer looking to explore the code base, build out your own predictive modeling pipeline, or perfect some other features, or inspect a real-time scheduling logic, the entire project is open source. I have documented every single layer in the repository's README, and everything is up there. The link to the full GitHub repository and Kaggle datasets are dropped right in the description box below. Go check it out, fork the code, clone it down, and start experimenting with it. If you like this video, please give it a thumbs up and subscribe to my channel.